None of that.
No, I can't have that on the recording. Right. Okay. Well, for some reason, I can't see myself full screen. I will just have to live with it. Never mind. We are recording, and so welcome everybody to the 11th talk. I've sent round two things. One are my notes for this talk, which, because they're speaker's notes, don't expect anything really sophisticated or finished. They're just to remind me what to say. But more importantly, I've sent round our paper with Colin Rourke, and that has been slightly tweaked to update certain things, and that is a very good reference, we think, anyway. So what are we going to talk about? I need to share the screen, and let's have a look. This is when I might have to go into my screen again. I don't know why. Share screen again. Okay. Now, what can you see?
A list of lectures.
A list of lectures, not the actual lecture.
Right.
This is what always happens, and I wit not why.
You haven't opened the document viewer, that's why.
How do I do that?
Double click on it.
See, I can see it. And now, why can't you see it? Maybe I should try again. Now, I'm going to stop recording for a bit. Well, no, there's no point. Share screen. See, all I get is a list of things. I don't know. It's really annoying.
If this is the future of universities, God help us.
Oh, well, all the students are slouching in now, so. Right, what can you see?
A directory listing.
Oh, a directory list. Why can't you see what I'm seeing?
No idea. I'm viewing Roger Fenn's screen.
Yeah, but I can, but that's not what I've got on my screen. On my screen, I've got this picture.
You're not on share screen. You're sharing a specific application window, so you have to stop sharing this application and start sharing a.
Okay, now it's gone.
You see, I can't see anywhere when I do the share screen. The what I can see, which is ridiculous. This happens every time. It's just.
Well, you must have learned how to do it then.
Well, except that we keep doing it and eventually it works.
Roger, are you the host of the meeting?
Well, I should be. Let's have a look.
Surely
Yeah, I'm the
you are.
host.
You set it up.
Yeah, I'm the host. So I don't know. I'm going to stop recording for a while. Okay, I'm recording now. Welcome to the 11th lecture on this. And let's see if share works. How's that?
Okay.
Good. Oh, so I want to talk today about quandles and racks. And as I said, I've sent round the paper I did with Colin some time ago now. And so that's where you can get all the details. This is just to sort of whet your appetite, really. So we've got a set X with a binary operation, which we're going to write exponentially. So the pair AB goes to A raised to B. And then we've got possible axioms. Axiom 1 says, given A in X, then A to the A is A. Given AB in X, there is a unique C such that A is C to the B. And given ABC, then this formula holds. What does this formula mean? Well, I've written it down here. A, B, C means do C onto A to the B. So in other words, I do B first on A and then I do C, whereas A to the BC means that I do BC and then do the result onto A. So that's the means we can dispense with brackets using this notation. But that's not the only notation. Oh, you'll notice, by the way, that the axioms, there are 3 axioms, rather like the 3 Reidemeister moves. Okay. This notation is asymmetric because we think of B as acting on A in the expression A to the B. But, you know, there's no reason why we can't use a more conventional notation. Say A to the B is A wedge B, right? So that can bring out other items. The picture to bear in mind is the following. We've got a crossing of some diagram. The arcs from the undercrossing to undercrossing are labeled from some set, this set X here. And as an arc goes underneath, giving a right-handed twist, the label Y becomes Y to the X. Okay, and notice that the undercrossing arc is not oriented. It doesn't have to be oriented. This is true for a right-handed crossing or a left-handed crossing. The only thing you have is that as you go under X in a right-handed way, it changes from Y to the X. Okay, so now let's look at the axioms in turn. Well, we have, start with axiom 2. Given A and B in X, there's a unique C in X such that A equals C to the B. Well, this is yet another binary operation. So C is A to the B bar. That's one notation. Or if you like, is A bar wedge B, right? So that's just another binary operation. And then they're inverse to each other. So A to the B, B bar is A to the bar, B bar B, which is A. Or if you like, those 2 operations cancel out. And of course, this is something to do with Reidemeister 2. So if you follow the labeling along, A changes under B to A to the B, and then because we're going this way around, or if you like, as you go under, you act by B bar. So you get A to the B, B bar, which is A. And similarly over here, if the directions go that way. Okay. So that's what axiom 2 does. What about axiom 1? Given a in x, then a to the a equals a. In other words, if we act by a bar, we see that a to the a bar is a. So this is a fixed point of both the actions if that axiom 1 holds. Okay, so this is the interpretation. A comes along here, it's the label on this arc, and it goes under a right-handed, it's the right-handed curl, it's the same with the left-handed one, and it changes to whatever it is here, x, and it becomes a to the x. Okay, but if we want it x to be a, you know, in other words, we don't care about the curl, want to get rid of it, Reidemeister 1, then we get a to the x is x, or if you like, a equals x. However, even if axiom 1 is false, suppose that we don't have, then we have a sort of curl cancellation. So a comes in like this, and it goes over x and becomes a to the x, okay, which is the same as x. And b comes in like this, it goes under x, so it comes b to the x, so a to the x is b to the x. Now, if we act on by x bar, that tells us that a equals b. So we haven't used axiom 1, we've just used axiom 2, and we see that these curls cancel out. I mean, we might just as well join this point to this point by a line and get rid of these 2 curls. Okay. Now, all axioms are born equal, but some axioms are more equal than others. And okay, they're all interesting, but axiom 3 is the most interesting. So when we've got given 3 elements, this is true, this formula a to the bc equals a, c, b to the c. Or if we write it out in wedge notation, we see that it's what's called right self-distributive or right distributive, RD. So C comes into the bracket, it acts on A, and it acts on B, and the 2 things are then wedged together, okay? And the same thing is true of bar wedge. It's the same thing, it's right distributive. And then the other thing we note is that if we've got this formula, B of, well, C acting on B, oh, sorry, BC, if we look at it in the next level up, it acts like a conjugate, like a bit like a group conjugate, C bar BC. In other words, so we can always reduce the top level. So an element such as AR, where R is some operator defined from elements of X, and this operator or the bar wedge or bar wedge, this can be reduced to A to W, where W is some word in X and X bar. All right, so all the elements of X together with the barred elements, okay? And this is the Reidemeister 3 interpretation. You see this one labeled A, as it goes up here, it becomes A to the B, and then it's acted upon by C, so it's A to the BC. On the other hand, over here, first of all, it's acted upon by C, so it becomes A to the C, but now in the meantime, B has changed and become B to the C, so we get A to the C to the BC. So that's the interpretation of Reidemeister 3 with this notation. You know, this axiom 3 is interesting. It's all over the place in mathematics, and if you think of, say, you've got a message going around the world on the web, and it's going to be changed some way. It's split up into lots of bits which are floating around the web, and they all have to be amended by some way, in some way. So we have this distributive action because it's got to act on all the bits as it goes round. So that's another way of looking at it. I haven't expressed that very well, but anyway. So here's some definitions, and I know you all love definitions. So a rack is a non-empty set X with a binary operation satisfying axioms 2 and 3. Okay. Quandle is a non-empty set X with a binary operation satisfying axioms 1, 2, and 3. Now, so in other words, a quandle is a rack which satisfies axiom 1. A spindle just satisfies axioms 1 and 3. I think you've been involved in spindles, haven't you, Lou? Or you're not sure? Okay. And a right shelf that's another name for right distributive axiom. A chi is a quandle which is involutive. So A, if you act upon it twice by something, so A to the B squared, you get back to where you were for A and B and X. And you can extend that. You can say an n quandle is a quandle such that A to the B acting upon n times is the same as A, okay, for A, B belonging to X. And so a little bit of history. So when I was working on this with Colin, this was 1991. Wow, a long time ago. Rafe, Gavin Rafe was one of my colleagues at University of Sussex, and he went to school with Conway, and he Rafe and Conway actually wrote something about I think it was a 2 quandle actually, and I have somewhere these letters they wrote to each other. But what we didn't know at the time was that a 2 quandle called a chi was introduced by Takasaki in 1943 in the Second World War. But anyway, so it only came out. We found out about that later. The most comprehensive published study of quandles in a topological context is due to Joyce. So really, he established a lot of the basic algebra of quandles, and he invented the name quandle. So he defines the fundamental quandle of a knot in S3, giving both the topological definition in terms of nooses and the definition in terms of presentation, which can be read from a diagram of the knot. He proves the equivalence of the 2 definitions. His main result is that the fundamental quandle classifies the knot, well, at least up to orientation. Joyce's work was largely duplicated independently by Matveyev, and he used the name distributive groupoid. Kaufman also studied racks using the name crystal, I think, for the concept. The most extensive algebraic survey of racks was given by Brice-Korn, who is particularly interested in the context of braids and singularities. His name for a rack is an automorphic set, which is it's a good name, but it's a bit long. So we've stuck with rack for various reasons, which you can see on the notes or on the paper anyway. Okay. So, well, we can make all these concepts into fundamental ones by taking a diagram of a knot and labeling the edges from one undercrossing to another undercrossing by some generator. These are called meridian generators. And then a relation for each crossing of this form, that as something goes underneath in the right-handed way, then it gets altered in that sense, okay? So let me do this example, the trefoil. The generators are X equals A, B, and C, so it's A, B, and C. And the relations are A to the C equals B, B to the A equals C, C to the B equals A, okay? So we can get rid of C and one relation to get two generators A and B, and two relations A to the BA equals B and B to the A B equals A. That's assuming that A to the A equals A, etc. But of course, if you're looking at the fundamental, that's for the fundamental quandle. If you're looking at the fundamental rack, then you won't have this relation and it won't be so nice. It'll depend on the framing which you get from the diagram, the framing of the knot. If you imagine, you see, when you're looking at racks, you must, well, there are two ways of looking at it. The traditional way, you look at a knot as a thickened tube, a torus, solid torus in space. Okay, so imagine that's a very thin tube. But if you're thinking of a rack, then you think of this as being a ribbon, and a ribbon can have twists in it, but we imagine that the ribbon is actually flat on the plane of the of the projection onto the plane. But of course, you can always twist a ribbon to give it a different framing. And of course, if you think of the ribbon, think of a cross section of the ribbon, it's an arc, a little arc, and then you thicken that up to become a disc. And so that would be the cross section of the knot in space. Okay, so that's the idea. And then we can get back to the fundamental group by putting each relation of this form equal to A to the I plus 1 is the conjugate of AI by AJ, okay? And we get this is the associated group of the quandle or rack. So in other words, we take a rack and we decide that we're going to convert all the actions into conjugations, and we get a group, okay? And this is the associated group. So we got the fundamental quandle or rack determines the fundamental group. But the longitudes are also determined, because if H from Q to Q dash is a homomorphism of quandles, then if we got something which fixes A, then H will take that fix into the image. Okay, so you know, if you've got a homomorphism quandles, it's going to respect the action here. So HA acted on by HL is the same as HA. Okay, where L is some word representing the longitude and A is a meridian generator. So by Waldhausen's theorem, which I talked about in the last lecture, this determines the knot because the meridians and the longitudes are all preserved. Okay, so that's, but the details are in the attached paper. Okay. And there's a topological interpretation of the fundamental quandle and rack. Okay, so we, just for simplicity, take a knot with one component in S3 and let MK be the complement three manifold with boundary a torus. Okay, so let star be a base point in the interior and let gamma be the space of homotopy classes of paths from the boundary of this three manifold to star. And then the homotopy, so what happens under this homotopy? Well, the endpoint at star, that's the final point of the the path is fixed, but the initial point of the path is allowed to wander at will over the boundary. Well, that's in the case of a quandle, but is restricted to a longitude in the case of a rack. Okay? So it's so you can see, so you somehow get that picture in your head. There's a map D from this set of homotopy classes of paths to the fundamental group using the meridian at the initial point. So in other words, you can, and pi1 of k acts on gamma, and gamma becomes a rack or quandle as follows. Okay, so this is the detail. Supposing A is represented by the path alpha and B is represented by the path beta in gamma, then A to the B is A acted upon by D of B. Remember now D of B is something in the fundamental group. So this is the composition, the following. You do alpha and then you do a beta backwards. So remember, alpha takes you from the boundary to the base point, and then beta takes you back again along the path beta, but backwards. Then you go round the meridian where beta has its initial point, and then you go back by beta. So you've got this composition here, and that tells you what the action is, and then you take the homotopy class of that. Okay, so that's the, and then it turns out that that's a rack or a quandle, and that defines, that's a topological interpretation of the fundamental quandle. Okay. So we've already seen that quandles are powerful. So here's a couple of theorems. The four quandle of the reef knot and granny knot are different. So there's a fundamental four quandle, just like there's a fundamental chi, or there's a fundamental three quandle, but the number of elements in the fundamental four quandle of a reef knot and granny knot are different. So these are different knots. And then this theorem, the fundamental chi detects the unknot. Now that's a deep theorem. Okay, I mean, easy enough that if you've got the unknot, then the fundamental chi will be trivial. Think about the opposite. I mean, we've already discussed the fact that if the fundamental group of a knot is the integers, then it's a trivial knot, but you need the deep result of Dane's lemma to prove that. Now, the fundamental chi, if that is trivial, like the unknot, how do we prove it's the unknot? Well, we have to take the twofold cover, and then we know by the Smith conjecture, which is a deep result, that any action orientation preserving homeomorphism of S3, which has some power equal to itself, right? So it's got torsion. Then the fixed point set is unknotted. So that's a deep result, and so this fact here is uses deep mathematics, and both due to Winker in his thesis. Is that right, Lou? I think that's correct.
Oh, right. I mean, Winker showed that the fundamental chi determines the fundamental group of the twofold branched covering, and then you can get to the Smith conjecture.
Yeah. Okay, and then there are many examples of racks and quandles, and I'm not going to go through all of them. We'll be here till doomsday, but it's all in the in the paper I've sent around. And of course, the obvious the most obvious one is conjugacy in a group. So here we have, and we can do it n times, and so that sort of makes it a bit more interesting, perhaps. And then there's something called the core. This is this core here, which is rather strange, and that sends G to the K is K, G inverse K. And it's, I don't know, slightly weird, but I don't know anything about it. And now we've got the Alexander rack, or quandle as it is in this case. So let lambda be the ring of Laurent polynomials with variable t and coefficients, the integers. Any lambda module m has the structure of a rack with this rule here. So a to the b, so a and b are in this lambda module, and so they can be acted upon by t, and well, in fact, acted upon by this character here. And what we get is t times a plus 1 minus t times b. And then you can easily check that that's a quandle. And if we let M be an affine space, and we let the action of t be multiplication by -1, this is yields a quandle defined by reflection in a point. So in fact, we put t equal to -1. So then we get 2 here. So we get minus a plus 2b. Okay, so that's reflection in a point, and that's that I think was Takasaki's original thing which he looked at. And then Coxeter take a symmetric bilinear form on Rn. S is the subset of Rn consisting of vectors V whose inner product is not 0. There is a rack structure defined by that formula. Geometrically, this is reflection. Well, I'm assuming in this case it is a reflection if we've got if this is the normal, the normal inner product, the Euclidean inner product, then we've got reflection in the hyperplane W such that W is orthogonal to V. Okay. Okay, here's the first of our questions. Now, I decided to give out questions from time to time, things which I haven't really thought about, so they might be wrong, and they might be right, and somebody might come up with an answer immediately. So this is question 1. Is the Grassmannian, which is K affine subspaces of Rn, a quandle? For instance, you can think of lines in R3, that's a space, and you can reflect one line in the other line. That might define a quandle action. I don't know. I haven't really thought about it because I wanted you all to think about it. What do you think, Lou?
I'll think about
it. Okay, now, one of the things which I did, I was having leave and I was in Madrid, and this was when I was working with Colin, and we used to communicate by fax, would you believe? This was in 91, I think, and that's because, well, we didn't have, was there email then? I don't know. But anyway, we were using a fax. And so I thought, well, you know, you could make a group into a space. Why can't you make a rack or a quandle into a space? So look at this square here. Okay, so this is kind of like a neighborhood of a crossing. And that defines this square. This is a square with a tile, if you like, with an imprint on it. A nice, very boring pattern, But anyway, there it is. And then let's generalize this. So we take x as a rack, and we take x to the n, and we call this is a name for an n cube. So to know what the boundary is of the n cube, the back I face is just obtained by deleting the ith element. So we go down the dimension, that's a face. And the front I face of A is defined as follows. Once again, we remove AI, but it lives on because it works on all the previous entries in this word, which defines the cube. So that gives us all the faces of this cube. And so you take all possible cubes and you start gluing them up according to these rules, okay? And you get a space. Infinite dimensional, it's built up of cubes. And here's my second question. Let's take X to be a free rack or quandle. You don't know what that is, or you might do, but I'm not going to tell you. It's in the notes. And is this space a cat zero space? What's a cat zero space? Well, look it up on the web. And so here's the question, which I think this one is true, but anyway, so that's my second question for today. Where are we now? Okay. So we've got this square, and if we've got a knot diagram, we've got lots of squares, and we can sort of put them all together and get a tiling of S2 with each tile has got the crossing in it, this square tile, and they're all glued together. So K defines a map from S2 to X to the N. Okay. In fact, it lies in the the 2 skeleton. Okay. And then the homotopy class, provided n is greater or equal to 3, only depends on the knot type and is made up of Reidemeister moves and cobordism moves. So this is what happens on a cube as you move. You push through three faces to other 3 faces in the cube, and if you look at it, it's a Reidemeister 3 move. And then we've got and it works because we have this relationship, A to the BC is A to the CBC, okay? All the other things fit together nicely. So that's homotopy across a free cube. And then we can have birth or death of a small loop labeled A, and we can do saddle or bridge moves as follows. Okay, so it's a little kind of like a cobordism. Right, now we come to cohomology. Okay, we've got a space X, so we could look at its homology and cohomology. I mean, back there, we were looking at pi 2, then that's interesting as well. But it's perhaps easier to look at homology and cohomology. So we take Cn to be the free abelian group with basis the n cubes and define the boundary map from Cn to Cn minus 1 bar on the basis elements, and then you extend by linearity. So the boundary of this is, so the alternating sum of the front face take away the back face, okay? So for example, if I do a 3 cube, the boundary of ABC, this cube here, is looking at this formula here, it's minus BC, so that cancels, that always happens. And then we're eliminating, so that's because we're eliminating A, and A, poor thing, has nothing to act on, so it's just that. But now we eliminate B, and B acts on A for the front face, but it vanishes for the back face. And Then we eliminate C. C works on A and then B. So that's the front face and that's the back face, and it becomes, so that's the formula for the boundary of the cube. So this defines rack homology and cohomology. For a quandle, there's a small tweak. An N cubed is called a quandle cube if two things are equal. AI is equal to AI plus 1 for some I. Okay, and then if you like, that's a kind of degenerate cube, and we let Dn be the subchain group of Cn generated by the quandle cubes, and now we replace Cn by Cn over Dn, and lots of people have worked on that. So that's it's amazing how much mathematics this is all generated. Okay. Right. What about biracks? Well, let's not restrict ourselves to one basic operation. Let's have two operations, A up B and A down B. So here we've got this square again, and this is the square AB. And now you notice in the previous one, we didn't care whether it was a positive crossing or a negative crossing. But for biracks and biquandles, as I said, we do have to worry about the orientation. And so A converts to A to the B as it goes under in this right-handed sense, and B goes backwards to B down A, all right? And then, so that happens for a positive crossing, labeled A and B, and for a negative crossing, A and B. So once again, A converts to A to the B as it goes under. This is in the right-handed sense. But B goes the other direction and becomes B down A. So that's a birack. Now, okay, that's all I want to show you today. But next week, I will talk about biracks and why we study them, or why I study them. We've got the fundamental quandle is a complete invariant, so why worry about the fundamental birack? You see, we can go through the same thing and define a birack or biquandle. You're not going to get any more information for a classical knot, and this is true. The biquandle doesn't give you any more information than the quandle. However, two things. Makes lots of nice algebra. Okay, maybe you like that, maybe you don't. Or if you study virtual knots, and I did mention virtual knots earlier, which we haven't really looked at. So we'll have another look at them. Then the biquandle is a very important invariant of virtual knots. Wouldn't you say, Lou?
Yeah, I agree.
Yeah. Okay. So we'll leave it there for now, and I'll stop recording. Well, wait a minute. Are there any questions? Scott, do you want to say something before you catch the train? Oh, you can't hear.
Hello?
I can hear, but I can't speak.
Oh, have you got the virus?
No, I don't have a microphone.
But we can hear you.
We can hear.
Oh,
Yeah.
okay. I didn't realize that. Yeah. Earlier you said something about a longitude, and I think you meant the longitude.
Well, there's lots of longitudes, and there's the longitude.
Right.
Okay, and the longitude is the one which spans the Seifert surface.
Right, but it had to do with the definition of the birack. Or of the rack, I'm sorry.
So
of
yeah.
the rack.
See, what normally does if you've got a planar diagram, then you take the longitude which you get from the diagram. In other words, you imagine
the blackboard framed longitude.
Yeah, blackboard frame. You imagine it's made out of a ribbon, and the ribbon doesn't have any twists.
Okay, so that's a longitude that you use.
Yeah, well, when you write down the presentation of the fundamental quandle from the diagram, that's what you get. But of course, you can always put some twists in to make the blackboard longitude the longitude.
Sure. Okay. The other comment I wanted to make was, so Brian spoke about the rack space in Warsaw. I think it was 1996. And I actually have notes on that, which I saved, which is remarkable. And then the quandle homology, Masahiko and I completely forgot this. And Masahiko and I started developing the quandle homology with Laurel Langford for reasons of categorification. We were looking at some of the obscure papers, I forgot the authors, and we realized that cocycles could be used to create invariants. And then we simplified them to quandle cocycles and sort of independently worked out what quandle homology should be. And I said, you know, this looks familiar. And I wound up looking through my Polish notes and found Brian's lecture there.
Okay.
Yeah.
So you invented it independently?
Yes. Yeah. But I mean, obviously something must have been there in the subconscious. It just hadn't registered.
Roger?
Yeah.
I'd like to ask you a question about the argument you sketched for why the fundamental quandle determines the knot group. It's a little different from Joyce's, which, as I recall, first showed that the group acts on the fundamental quandle, and it's.
You must remember that was just a sketch.
But is your condition equivalent to the fundamental group being the fixed point group of any element of the quandle? You talked about homomorphisms.
Well, I've only just sketched what the proof is. If you want to see the proper proof, go to the paper.
Okay.
Yeah. I was just trying to give a sort of overall impression of how it works.
Another comment is that the quandle all by itself doesn't distinguish mirror images. So we have to be careful about the statement that it classifies the knot.
Yeah, well, I will say up to homeomorphism.
Yeah.
Or up to orientation, sorry. Yeah.
But when you generalize to the rack space, you do get a classification of knots, right?
Well, classification is a very big word.
Well, I mean, in principle, you distinguish mirror images using the rack space, don't you?
Oh, well, you can. Yes, using the rack space, you can. That's correct. Yes, you have to use. I think, if I remember correctly, the pi2 is the integers of the fundamental rack, and so we've got a plus or a minus one. I think that Colin would be able to correct me on this if I get it wrong. That the knot, which is labeled by its own fundamental rack, defines a generator of pi2, which is plus or minus 1. And so that's, I don't know if we've ever written that out anywhere, but it's should be true. I think we did prove it. Yeah.
Oh, another question about
Yeah.
the words. Conway and Wraith called it the WRACK.
That's right. Yeah.
And you guys removed the W. I always thought that was amusing.
Well, because both names are co-name. I mean, they're both from the same root. You know, Warak and Rack.
Right.
And of course, Conway used it amusingly because of Wraith's name. So, I mean, the idea of a rack is that it's the wreckage left behind when you go to rack and ruin, and so it's what's left behind when you ignore the multiplication and just use conjugation.
Did you ever have a conversation with Conway about these terms?
No.
Oh.
No. The only time I tried to interest Conway in my work was with doodles, and he didn't seem to be very interested. So that's my only contact with Conway. Well, if there are no more questions, I guess I'll stop. And the next talk will be on Tuesday, 12th in the series. I think it's Lou's 6th talk. Tuesday, 6 o'clock, some British Summer Mean Time, which is GMT +1. So hope to see you there. I'm going to stop now. Bye.
Thank you, Roger.
Thank you, Roger.
Okay.